So in the examples we've looked at so far, for example, when we're considering this problem where you're applying a little bit of a load and increase that load and look at what happens to the friction force that's resisting that load to keep it in static equilibrium, we were looking at a horizontal applied load. Similarly, in this problem here, looking at a horizontal applied load. What we're doing here is we're looking at a situation where we've got an inclined applied load. Now, it could be pointing downwards, could be pointing upwards, but either way, it's going to change this normal force. So if you had a force that was pointing upwards, just have a look at, where's my pen? So if we had, rather than this downwards force, we could add an upwards force. What we'll find is that's going to reduce this normal force, and a downwards force is going to increase this normal force. So what we have to do in these situations, we have to look similar to what we did here, except a little bit simpler. We have to look at what are the components of this applied load normal to this surface and aligned with this surface. And so let's have a look at that in this case. So we still got a weight component. So let us do that. So we're told, so let's just call this W. So we're told that the crate has a mass of 20 kilos. Let me just check I'm 100% zoomed. So therefore we're going to get our W is going to be equal to mass times gravity, which is equal to 20 kilograms times 9.81, which is going to be 19.62, I think, newtons, 196.2, sorry, 20 kilograms. So it's going to be 190. Sometimes my hand doesn't do what I'm thinking. 196.2 newtons. Now, so we know what that is, that force there is. Then we're going to think about this force here, and it's going to have two components. And so it's going to have one component that's acting horizontally, parallel to the surface, so like so. And we know that that angle is 30 degrees. Just think about where I'm going to put that so it doesn't get in the way. So that's going to be 30 degrees. And we're also going to have, if we're doing nose to tail, so we must have a vertical component here as well, like so. But its actual point of application will be over here. And this would be, let's have a think, what do we want to call that P? So we'll call this PY and PX. So then let's just figure out what those would be. So PY is going to be sine 30, so it's going to be 80 newtons sine 30 degrees, which is just going to be 40 newtons, and it's going downwards. And then Px is equal to 80 cos 30 degrees, which is just equal to, so 80 times cos 30 is 69.28, so 69.28 newtons, and it's going right, left to right. Just check those. Just take the square root of the squares of those just to make sure. So 40 squared root of 40 squared plus 69.28 squared is equal to 80. Okay, so we've got those okay. Now what do we have to do next? So what we're trying to do is we're trying to figure out whether this is going to slip or not. Now, until, let's grab that drawing again. Here it is. I shouldn't really call this Fs, we should just call this F, just for now. So we're going to get some frictional force F. So what we can do is we can figure out, we'd need, for static, we're not worrying about moments yet, that's the next example, I promise. But we do need that for static equilibrium, we would need the situation where sum of the y components of 4, or let's say the x components of force, is equal to 0. So that means that Px, which is going in the positive direction, Px this way, minus F is equal to 0. So force is just equal to px. The magnitude of this force is just equal to this. And so that would be, so that must be equal to 69.28. Yep, 69.28 newtons for static equilibrium. Now, then what we can do is we can figure out what this here would be, this Fs, the limiting value of that friction for the normal force that we've got here. And so we can say, look, we can figure out this normal force because we must also have the sum of the y components is equal to 0. So sum of y components must also be equal to 0. So that means, so let's see what we've got here. We've got py down the way. So we've got py, and let's say it's negative. We could decide which way we put our x and y axes, but let's just keep them the standard way and just show it so people know what we're talking about. So we're going to have x that positive that way, y positive that way. And so we are going to get negative py, negative the weight, plus n equals 0, and I think that's all the y components. That's why I drew this one dashed, so I wouldn't do it twice. So therefore, the normal force is just equal to py plus the weight, which is just equal to 40 plus 196.2, which is 236.2 newtons down. Then we can figure out this limiting value of friction because that is just equal to, Fs is just equal to the static coefficient of friction times the normal force, which is just going to be, what was the static coefficient? 0.3. So 0.3 times 236.2, which is equal to, so 0.3 times 236.2 was 70.86. So that's 70.86 newtons. Now, so that's the limiting value of friction for this normal force. So the normal force is higher than just the weight because we've got this force pushing down the way. That adds a downwards component onto this crate, and therefore your normal force increases a little bit. And so for that normal force, it would be 236.2 newtons. The maximum frictional force you can get from that, you just multiply the normal force by the coefficient of friction, is 70.86 newtons. The force we need for static equilibrium is 69.28 newtons. And so it would just be in static equilibrium. So if the frictional force that we need is less than the static friction, which is the maximum friction you can get for that normal force, therefore crate will not slip. But we could say, but close to doing so. It's very close to slipping, so just a little bit more force and it would slip. Okay, so that's that one there. Now if this force was the other way up, we'd end up with a py component upwards, and so we'd end up reducing n, in which case it would definitely slip. You know, if this was 18 newtons and it was 30 degrees upwards, then it would definitely slip. And what did the question actually ask? Determine if the crate will slide or not, so we've done that. So the crate will not slip or slide, but it's close to slipping, so then we just underline our answer. We're done. Okay, let's look at one more example, and this time we are going to think about the moments and whether it's going to tip or not.